But you end up with more carbon than you need. The other part is that you're reducing or getting rid of the silicon, and oxidizes actually carbon silicates, which comes out as slack at the end of the day. So this is, you can tell by the temperatures here, this is something I feel very comfortable with, sitting there and visit my cousin very frequently. So this would be good. Okay. Now, but how we go further through hell is kind of difficult. There's complicated maps which tell us a little bit how to guide our path further, and we call those phase diagrams. So somehow this is our product from the blast furnace. We end up with raw iron, which is not really that useful, and we want to end up with something like a steel product, which has much lower carbon content. And so somehow we have to figure out going from here to here. It turns out there's a shortcut, and we can really just do this shortcut and we don't have to go follow any of the other paths. But it's quite nice. But in order to use the shortcut, we have to realize where we are, and a good milestone marker on our map are the structures of our product. So when we look at the microstructures of our product from steel making as a cast iron, this is what it looks like. It's called ladyburite, and looks pretty like a screensaver kind of. But we can see sort of this a cross section of our Christmas tree, which we call dendrites. The white stuff is cementite, and the brown stuff is pearlite, and so that's the white cast iron as it comes out of the blast furnace. If you cool it a little slower, we end up with gray cast iron, which has graphite, perlite, and some ferrite present. And if you add a little bit of magnesium, we end up with a malleable gray cast iron, where the graphite is in a spherical shape, which has a much better ductile properties because those don't act as crack initiators. But really what we want to end up with steel, which is a much different microstructure, which has this perlite structure and some ferrite, much less carbon, no graphite present. Or a heat-treated steel, which is martensite, or eventually austenitic stainless steel, which is what this large part of our reactors are made of. So our map tells us how to get there, and so we have to go through several more gates of hell in order to actually make that happen. So how do we get there? How do we get the next gate? Well, I would say we drive there. And that's also what the steel does. In fact, from the blast furnace to the further converters, they're driven in the liquid form, oftentimes from plant to plant. They have these torpedo rail cars, which are filled with liquid raw iron, and they're transporting by rail. As you can see in this instance, Nippon Steel does this and transport it to the next plant just in a liquid form, around 1300 C hot. Now, once it arrives, we open the next gate of hell, which is the LD process. LD stands for Lindstonovitz process, where we take out the excess carbon from our phase diagram to refine it further to steel. Now, in order to do that, we put in our liquid raw iron, some scrap metal, as you can see, and eventually add some more oxygen, which produces raw steel plus some slag. Here you can see the oxygen blowing to make it real hot. You actually need scrap metal, scrap steel, in order to cool the process, because this is a highly exothermic process, and melting some pure refined iron cools the whole thing. So if you melt this, you take away the melt enthalpy from the process and cool the whole converter that way. So you really need scrap metal to do that, which has some other implications, because if you put scrap metal into steel production, you end up with some impurities scrap metal might have, like copper or sometimes radioactive sources people are not removing. We do this in order to remove mostly the carbon, and about 15 minutes during this process, you remove most of the carbon. Phosphorus, silicon, manganese, according to those chemical reactions. And so we remove the excess carbon by essentially adding oxygen and removing that carbon in the form of CO2. Of course, oxidizing a little bit of our iron, but that's tolerable. Most importantly, remove some of the silicon, manganese, and particularly sulfur, which is very sad for me. I like sulfur. It smells so good. It's really, really nice. Now, so we have our raw iron after going through these chemical processes, but it's not quite an alloy. It's not stainless steel yet. So what we have to do is we take our liquid steel, or raw steel, and sometimes it can be sometimes, and you can use an electric arc furnace to start alloying various alloying elements. And this is actually done here in Berkeley. So whoever comes with me to the field trip to the steel plant down on 4th Street, that's where you're going to see how they actually alloy the steel and then cast it into various shapes and forms. And I know Hosman still owes you the date and things like that, but I will talk to him and we'll figure that out. And you have to be really careful because otherwise this person may end up like this person. And that's not very good for your alloy because who knows what's in this, right? I mean, you want to add alloying elements which are appropriate for the steel you want to make, not some random hatch patch of scrap metal. So once you have your metal alloyed, now you cannot have it liquid, which is great, but eventually you want to pour it into a state and a shape and a form you kind of want to use it. Now today there's a very nice process called continuous casting, where one pours in the molten steel here, and interesting is you pour it essentially in an open form, and it solidifies just on the outside skin and stays liquid in the center. And only as it is extruded further down, you actually it solidifies on the inside. So the liquid core stays liquid for quite a while, and you can make endless products that way. Rods.
How do you get started?
That's a good question. You put a plug in there originally, and fill it up, and then pull out the plug slowly, and have it solidify that way. It's a good question. I asked the same question actually. And there's so you can do this with various metals that way. It looks pretty cool. So you can do this. This is my like hellish rods, I guess, and they come right out there. But for nuclear components where you need a lot of mass, maybe block casting is a little bit more appropriate, where you need a big block of material to start with. Which is great. Now we have a block or a rod, but how do we end up with a reactor pressure vessel or similar? Now, forging, even though people have been forging since 3,000 years and fundamentally nothing changed, it's still done today. And this is a fantastic show here. This is actually the second largest forging press there is. 13,000 tons at CAP Steel in Korea. They're the big heavy duty forging are all in either Japan, China, France, Russia, or Korea. There's actually none here. So if you wanted to order something in the order of 650 ton component, you would have to go to one of those countries. It's a long movie, I'm not going to show all of it, but what you want to pay attention to is when the people walk by. So you kind of sort of see the scale a little bit of these things. About 600 to 6, here's a person. So it's about 6 feet diameter or something like this. And about 650 tons or so is about what you need for a reactor pressure vessel. Because you lose quite a bit due to oxidation, which is the black stuff which keeps falling down here every so often. So that's quite impressive seeing these things in action. All right, so we shape our material, and I do want to point out that there are exciting new ways maybe of how to make not those kind of large components, but smaller components, which are also a pretty awful process, to be honest. But it would be additive manufacturing, where you use a laser to heat things up, and you blow in powder at the same time, and you can not quite, but to some extent, make a quite different number of shapes and forms you want to do, and build them out from scratch. So you don't have to do the forging process or anything. All you need is some powder and high power laser beam to do so. And that creates quite a nice number new routes you can use this for. So in this instance, they make gas turbine blades here like this. Now, I do want to highlight from one of my students, Krampus' students, the work that you could use this technique now, which is something really exciting, that you could now grade functional graded component. Let's assume this is how you would have made it conventionally of two materials, and this would be sort of an optimized design, and you could now grade the function of a property of a material that way. And you could start with a material which has material A on one end and material B on the other end, and you just create a compositional gradient as the part requires. So you have something which is hard on one end and soft on the other end, or some other properties. And so Ashley, true servants to Krampus, is making these parts with industrial vendors and create properties, different properties as a function of location of one part, which go hand in hand with different microstructures, where you have a very hard BCC, FCC mixed material and a stainless steel on the other, and you can tailor the shape to the property. So that's kind of exciting upcoming things with this type of shortcuts we have. Now, important question, however, is then the seventh gate of hell, right? It's our favorite one since we're in the nuclear engineering department, which is truly the nuclear application. So we have in the seventh gate of hell, the material experiences stress, the environment, and the radiation, which is causing stress corrosion cracking, corrosion, radiation, induced stress corrosion cracking, swelling, creep, fracture, what have you. And the material in service supposedly has to last through these conditions. And that is obviously a challenging process. So we went through hell in order to get to even worse places, which is the nuclear application. Now there is salvation, and we can fix it. So St. Nicholas can bring salvation through science. So if you really understand what we're doing, Krampus is going away and St. Nicholas gives us chocolate. And where's Sarah? She gave us a bunch of chocolate here, so we can pick that up later. Now, an example where science really helped us a lot is something everybody in the instance used, at least most people use, is people who fly with airplanes or gas turbines or similar things. So we really tried to understand since the 60s the degradation mechanism of materials at high temperatures, and what that led us to is improvements of service temperatures of various materials. And if you just stay with the normal materials development process, I want to point you to this number. If you take this time period and the degrees Celsius improvement you got, you come out with 4 degrees a year. Right? So we got about 4 degrees a year better in service temperature of material, which is really not that much. But at some point, people introduced game changers, like in this instance, thermal barrier coatings, or silicon-based ceramic components, SIG components, for example. And at the point, you can raise the service temperature significantly. So you as engineers, I want to point you to this, say, well, if you can do sort of business a little bit as usual, and we can do 4 degree a year change, that's good, that's exciting. But what you really want is this, right? You want to kind of improve the application and the use through some innovative thinking and innovative material science in this instance. But in order to get there, you really have to understand the mechanisms degrading your service condition. If you don't understand your mechanism, you will never know how to get there. So the Berkeley Materials Research Group is addressing all this comprehensively via environmental degradation, radiation damage, and alloy instrument development or materials development processes. And so what we do here, we look at light water reactor corrosion issues or advanced reactor corrosion issues, liquid metal corrosion mostly. Particularly interesting radiation damage causing microstructural changes and mechanical property changes. And then we can also try to develop new alloys, maybe introduce silicon carbide composites, maybe go to nanoscale precipitated materials or similar. And so we're trying to address this comprehensively in order to not burn the Golden Gate Bridge down, but rather build the Golden Gate Bridge and trying to understand all the scaling mechanisms from the large scale to the small scale, from atomic to application. the structure as well as the property, and try to do this in this way. Now, there's plenty of scientists doing this work here in Berkeley. I want to highlight particular our junior scientists, undergrad students who help us. Really, we couldn't do any of the work without them. Of course, I also want to acknowledge the senior scientists. I hope I didn't forget anybody. But really, the boss is Marie. She's a minion today. So, anyway. And so all these scientists doing the work guided by the minion, boss minion. And I just want to highlight a couple of examples of what it is that we can learn and can do. One is we take this devil here, which is the this devil here, and we want to squeeze him in order to test how strong he is, right? And we can do this in situ via mechanical testing on the micron scale. So this scale bar here is 5 micrometers. Keep in mind the diameter of a human blood cell is about 5 microns, red blood cell. So you can do a mechanical test, assess the strength change and the work hardenability and failure mode on something which is as small as your blood cell. And that's exciting because that way we can cut down on contamination and radiation and hazards and things like that quite a bit. What I want to point to is that this failed significant difference. You could see this one fail here in the sudden motion, which is the aerated one. Oopsie. Aerated one, or this one didn't fail, which is the unaerated one. Those arrows actually point somehow at one. But anyway. Now, you can. What happened to my little devil? Okay. You can also do this in tension, which is quite exciting because when we started this, I did not think that you can get a reasonable strain measurement out of a scale which is half the size of a human blood cell. I did not think that you get actually reasonable numbers and comparable numbers. However, indeed you do. The unaerated case, you see something like 40% elongation on a stainless steel, which is typically for stainless steel unaerated. But once you irradiate it, you end up with something like less than 10% total elongation, which is what typically you get with radiation damage. And that's kind of interesting that you see that. So I was super happy. It's interesting to point out, however, you may have noticed these load drops here, these drops in load over the different strain, and you can actually do quite a good job in analyzing these load drops. And each load drop, actually, you can quantify the energy it takes, the energy released during this sudden deformation motion. And if you put a little bit thought into this, and some equations, which I'm happy to explain, but I'm sort of running out of time a little bit. Happy to explain. You put a little bit of thought into this. You can estimate that in your unaerated case, you should see something like a 40 nanometer type step height. And in the aerated case, you should see something like a 600 nanometer step height. And when you look at these deformed structures, this is the unaerated one, and so they're much finer, much smaller, sort of in the tens of nanometer range, versus the aerated one has one very large one in this instance, which is sort of in the hundreds of nanometer range. So with a little bit thinking, we can actually really understand what's making these severe, I don't want to call it brittle, but sudden failure of a structure after radiation than before radiation. Another sort of highlight I want to point to is the fact that today we have tools where you can shoot various ions at things. And so you can take the zombie, and you really don't want the zombie to come near you. So you shoot helium at him, gallium, platinum, or other things at him, just to make him fall over. But if you do this, you can take your material and create these type of nanostructures and blow, for example, helium in each one of those and to different doses. And what you learn is that the helium actually creates sort of a superlattice, nano superlattice of little devils, helium bubbles. And they're in a regular arrangement, so you can do a fast Fourier transformation of this image, find peaks, and so you can measure what the distance is between all these individual helium bubbles and so on. And that's not new, that has been found before. But what is interesting, that with this implantation mode, if you watch how the deformation happens with this implantation, this is the not implanted material, and we don't see a sudden twin, versus here, we saw a sudden twin with implanted material. So this material starts twinning, it's the same material, except this one is helium implanted, and this one does not do twinning, it has not been implanted. So twinning, helium implantation induces twinning, which is a separate deformation mode in material, which typically it doesn't do. Typically materials deform by dislocation motion. In this instance, it deforms by twin formation, which is kind of different. And most exciting to me is the fact that if you have this type of twin structure, which is a folded lattice, then you can also see that the helium bubble superlattice rotated with this twin. So this twin causes 60-degree rotation of the host copper lattice, but it also rotated our helium bubbles. The question is, how do these nanoscale helium bubbles flip over? How did they suddenly just flip and change their orientation? How does this happen? The way this may happen is if you have your lattice and you have your helium bubbles here, and you pass partial dislocations through, and you assume these dislocations cut through the helium bubbles, then you would assume each helium bubble is getting moved by half a Burgers vector due to that cutting process, which eventually leads to like the rotated lattice, but also to the rotated helium bubbles. So this is sort of fundamental, but kind of fun to do because you can sort of flip things over, basically, or cut them in half. Lastly, I do want to point to another technique we can use to look at things. So essentially, we want to shock the material and rip its head off, and I mean this literally. So we have the atoms in here. Here's our metal atoms, and we shock them with the laser pulse, or sometimes with the voltage pulse, and we rip the atoms off the material. And how long it takes from the atom to hit the detector tells us what isotope it was. Where it hits the detector tells us where it was sitting in that structure originally. And so we can create 3D maps of various isotopes in a material. So in this instance, this is work done by Nathan Bailey, a graduate student who just graduated. We look at chromium, titanium, in this case plotted titanium oxide separately, moly, silicon, and whatnot. Irradiated at different temperatures and different doses, and what we can learn from this is that if you do an irradiation of this material at low temperatures, you form these chromium clusters. If you do this at higher temperatures, there's hardly any chromium clusters, particularly not above 412 degrees Celsius. We don't see any chromium clusters any longer. The chromium clusters are bad because they make our material more brittle than it needs to be. And so we need to understand when do they form so the material doesn't turn so bad. We also see other clusters like oxides and so on and so forth, enrichments and grain boundaries in 3D, and not just elemental but also isotopic specific. One thing, however, is an interesting question, and that's more to the math visitors here. When is a cluster a cluster? When do you actually say this is now a cluster, and when do you say it's not a cluster? So if there's various algorithms you can play with, and one is maximum separation method. So if this is your raw data set, well, you say obviously here's a cluster, but how do I tell my code that this is a cluster, and where exactly do I tell it that it ends? Is it here, or is it here, or where does my cluster end? What's the actual boundary condition? Well, I can do this arbitrarily and say, well, if it's like less than 10%, it's not a cluster, and if it's more than 10%, it is a cluster. All right, fine. But that's not really scientific. So you can use, for example, various mathematical methods, including the maximum separation method. We're trying to assess this, and depending what parameter you're using, you can get different answers. So if you use here this parameter, order 2, meaning how many atoms are within a certain distance of this D max, you split up one cluster into many individual clusters, which is not really what you want. was this here, but here you start getting somewhere. This seems to be more representative of that, and now you can start counting those things. And so that's actually kind of quite a bit challenging to do this right. It's not that easy. So with that, I would like to summarize my very, very, very brief introduction of materials through hell. And I hope you learned that there are 7 gates of hell. And you learned that manufacturing engineering materials is an evil and painful process with lots of heat. There are shortcuts through hell emerging, and they are very exciting. But eventually, we still have to go through hell to get there, really. It's truly a diabolic environment, and so hopefully we learned something why material science is important. And I wish you all happy Halloween. This is the material scientists and the nuclear engineers and all the people who make nuclear power plants work, and this is the people who want to destroy it. If you have no questions, I have 2 movies. Well, actually, let me show you. Does everybody know who Krampus is? Yeah. Show us a movie. All right. I'm going to show you a movie here. Let's see.
We're so happy in the holiday period and come around. We're talking about the difference between the United States and Austria. We have a couple of traditions. Enormous. The universe.
Can you guys hear that?
Because I think we have, we're not a league.
It's pretty hot in hell.
Peter, it's you.
For instance, we have this here, this guy. Hey y'all. That's what Elf on the Shelf says.
I missed this.
Hey y'all. And what he does is we have a thing Elf on the Shelf. What he does is he shows up at all of your house, and he you don't know where he's going to show up, and he will tell on you if you're naughty. So he goes back to the North Pole every night and tells on the kids if they're naughty. I suppose that's where it starts. Well, I mean, that's not where it starts. Where it starts and ends. It's fun. He's a cute little elf, and everyone has a good time. He looks like a wimp. He's an elf, and he's a full-grown elf, and that's what elves look like. He's cheery and holiday and festive and fun. Now, what do you have in Austria?
Well, Christmas is a different thing. We have sort of the precursor to Santa Claus on the 6th of December. St. Nicholas, that's the day, and on the eve of that day, we do the proper thing. It's a Catholic country, it works through traumatization, and we try to keep kids in order, in their place, and we have Krampus.
Now, guys, this is not a made-up thing. They have Krampus.
If you want Krampus, yeah.
Krampus, yes. Yeah, I apologize. And so Krampus, what does Krampus do now to the kids? He's just on a, he hides around the house. Sorry.
He's St. Nicholas's assistant, meaning, we look at the flip side, sort of the dialectic approach. St. Nicholas comes with praise and presence and wisdom. Krampus with a stick, a bag, and he threatens you with, if you weren't good, you get stuck in the bag and get
It's true, by the way.
Now look, honestly, even that description, as bad as that is, wouldn't be that bad, except we actually got a Krampus doll. And this is I'm not making this up. You ready to see what Krampus looks like? That's it. I'm not joking. That's Krampus.
I'm not joking either.
No, this is we researched. This is St. Nicholas and Krampus, Eve of December 5th. That's the real thing, you guys. Look at this thing.
You have to remember Sigmund Freud was.
Hey y'all. Hey y'all. Y'all ready to have happy holidays? Good.
skin that looks like that, only white, and masks like that, huge carved wooden masks, cowbells. They get drunk, not necessarily in that order. They get drunk. Storm like the riders of the apocalypse through the village, and
Krampus con?
yes.
They have Krampus. What's Friday being in the hallway?
Alright. So I take any Krampus takes any questions while I have this one running sort of in the background. Tell you what this kind of is going on there. It's pretty bad. So, yeah, it's KrampusCon. So
KrampusCon.
yeah. Yes.
So does Krampus like actually take kids? Like if you're a parent and your kid's being like really out of control, would you actually shove your kid in like a sack and hit him?
I can't tell you this much. I'm not going to do it with my daughter, but I'm not going to tell you if it happened to me.
Your daughter's good looking.
Well, I just realized, the scales have fallen from my eyes, why I was hired as department chair. My birthday is December the 5th. Here, so
There you go.
I'm the bad guy. I'm the Arnold Schwarzenegger here.
Any other questions? Anybody?
So Peter,
Yeah.
so you had this wonderful movie when you did the bladesmithing,
Uh-huh.
where you got your ore from the surface by picking up magnetite and separating it magnetically. Did any cultures ever do that on a large scale?
Yeah,
Who?
Japan, they found some. Some of the swords there were made that way. Actually, the first iron production is too much. The first iron-based products, I guess, were made out of meteors because you find them on the surface. And still today, people actually buy meteors online and forge them into meteor knives and things like that. Meteor microsects is super interesting. It's actually very unique because it solidifies its face very different than it does anywhere else. So it got its own name, Wittmann-Steffen structure, and it was originally found in meteors, and so that was found on the surface. And then some of the sands, some of the ores on the surface in the air.
Okay.
Yes.
Before the arrival of plants on the Earth, there was no oxygen, and so metals weren't oxides; they were just metallic metals. Was there any mineralization that went on during that period? Because it wasn't that long, about 1 billion years ago.
Well, so there was no oxygen in pure form. There is oxygen as an oxide, right? And sand.
And
It's
carbon
silicon
dioxide. It was
oxide,
carbon
right?
dioxide atmosphere.
And carbon dioxide, and so saying they were probably still oxides in many instances. I mean, I'm not a astrophysicist. Or
Don't the oxides like to float to the top of the molten? So you've got
Yeah.
a crust of
Yeah.
oxygen, and all your noble metals wanted to be in the center. So no platinum in the crust. Very little platinum in the crust.
Well, so that's true. The oxides float on top of liquids, right, at lower density. And that's why the slag floats on top of things. How the geology exactly works, because as this draws it back in and comes back out, I wouldn't want to speculate since that's not my area of expertise. But you find sand and whatever you find on the moon is similar. It's all oxides, right? So silicon oxide and magnesium oxide, whatever oxides you may have. Oxide tends to be the most stable form, and if there's any oxygen anywhere, it's going to grab it eventually.
So with the materials that have a gradient from soft to hard and all the properties in between, is it only going to be as strong as its weakest link? I feel like there's going to be one.
It depends what the application is, right? If you use it as a chain, right? Most certainly. But it depends what you want from it, right? So in some instances you would want their resistance at some location where there's a lot of friction, but maybe ductility somewhere else where you have a lot of torque going for it. Or in this particular application, it's about the magnetic properties. You want certain magnetic properties in one region, not so magnetic in other regions, depending on what the application is. Not everything is about strength. In fact, we as materials people, we can make things very strong. That's not the problem. We can make things stronger than we ever needed to. The problem is really making strong and tough at the same time, and that's hard. Toughness is much more difficult parameter to achieve than strength. So it really depends on the application.
Speaking of versatile, tell us about miraging steels.
Miraging steel?
Yes. What do you make?
Miraging steel is quite interesting product. It's not that old. I would say maybe a couple of decades, maybe too long. So you can buy it in the store. It's hard. It's essentially advanced tool steels. Some of those are actually export controlled because they use them for building things you shouldn't be building. They essentially are oftentimes iron-based, and what you do is you do a first heat treatment where you bring all the elements in solution and cause a Martin City. I can show you the picture. I should show you the picture, but I like that Krampus movie. We form a Martin City microstructure, which is a high dislocation density microstructure, and then you bring it into shape and form, almost in the final form and shape, grind it and so on, still soft, relatively speaking. And then you stick it in the furnace at 400 C to 500 C for a couple of hours, and it doubles, triples its strength. Just by the fact that you just allow the right elements to diffuse the right distance, and that forms nanoscale precipitates, and that about doubles or triples the strength of it. And the nice thing about it is it doesn't go with a not a major geometrical change anymore. Otherwise, if you do a heat treatment, you take your steel, stab somebody, cool in blood, and all that. The seen in movies, you get a shape change because this Martin City phase transformation is too much of a volume change and change shape. But in miraging steels, it's not the case, so it stays near that shape, which is a really attractive property. So, but it's quite an exciting material. Very strong, about 2,000 megapascal yield strength. Too strong in some instances. Yep.
On those stress and strain curves, what were those lines again? I think you kind of mentioned.
Yeah, the load drops.
Yeah.
So what happens? It's a little slow. These things, right? When there's real data. Yeah. So what happens is because the sample is so small, it's essentially a single crystal sample. Once you have a dislocation moving, it moves through the material without much of a hurdle. And so as the dislocation moves through it, it suddenly gets longer by that amount, right? But the tool is not fast enough to catch up with the slack in the sudden deformation, so it leads to this load drop. Right? The drop is an artifact of the tool. What the actual physics is this is slow. I have too many animations in here. Is actually a change in displacement. A sudden change in displacement is the actual physics because it's suddenly longer. But because the tool has a feedback loop and slack in the hole, you have to accelerate masses of the tool and so on. That leads to this drop at the end, and that marks the end of this behavior. But it's essentially, fundamentally, it is the dislocation is running through the system. Now, if you have something which has not been irradiated, you can see few dislocations at once, 10 break loads, maybe a couple of hundred break loads, which leads to very small load drops and small slip steps. If you have it irradiated, the dislocations pile up, and it takes a lot of energy to make them move. But once they go, they all go. And therefore, you see these very sudden, very large load drops in irradiated material, which leads to localized failure, which is what we're really afraid of in nuclear applications, is localized failure. We can deal with like strain and ductility and all that, but localized failure is killing you. That's what you don't want. And that's bad. So if you understand the slip step systems and the way they move and all that, how the way they pile up and the grain boundaries and how much energy does it actually take to break them loose, you have an understanding of one of the worst failure mechanisms you can envision in the nuclear material, which is sudden localized fracture.
Further questions? Let's thank Krampus again.